And just like we learned earlier in this unit, all of the parent graphs for exponential graphs, we need to be able to graph all of the parent graphs of log graphs. And so all log graphs are going to have the same basic shape, just like exponential graphs all have the same basic shape. The only thing that's going to change in your parent graph is that base. So this one's a base 4. Now at the beginning, when you're trying to think of what does a log graph look like, you're going to think about the same base with an exponential graph and do the inverse. So if I had a 4 to the x graph, I know that it looks like this. I know that it goes through 0, 1 and 1, 4. And I know that it has an asymptote at y equals 0. Now when I go to graph my log graph, it's just the inverse. So at the beginning, you're going to think about your 4 to the x graph and say, that graph has 0, 1. What is my log graph going to have? Switch the x and y. It's going to have 1, 0. And I have the point 1, 4, so my log graph is going to have 4, 1. Eventually, you'll just know that all log graphs have 1, 0, and whatever their base is, 1. So if it was a log base 7 of x, you would have 1, 0, and 7, 1. If you had a log base 3 of x, you'd have 1, 0, and 3, 1. And just like this has an asymptote at y equals 0, if you switch x and y, you now have an asymptote at x equals 0. So this is our parent graph, y equals log base 4 of x. And we're going to do all the transformations that we did in chapter 3, that we did earlier with our exponential graphs. We're going to do all of those with our log graphs as well. And it'll be the same idea, go from left to right, do your stretches first, then do your translations, and look at what happens to your asymptote. So do we have any intercepts? Well, all log graphs will have an x-intercept at 1. All log graphs will have x equals 0 as an asymptote. And if you think about the domain and range of our exponential up here, the domain was everything, and the range was greater than 0, then for our inverse, your x and y's get switched for domain and range as well. So now our domain is x is bigger than 0, and our range is everything. So now we should be able to graph every single log no matter what the base is. Now I think you have some space on the page 378 at the bottom there. Is there some empty space? In that empty space, I'm going to get you to graph y equals the natural log of x. Now, the log of x, the common log when nothing's written, has a base of 10. This is the natural log. The natural log is also a special logarithm where the base isn't written. Any guesses what the base of the natural log is? It's not 1. It's not 0. It's not pi. It's e. Log base e of x is the natural log. And it's written ln. The n stands for natural. The L stands for logarithm. I think it came from French, or they would say that backwards. And so we have y equals the natural log of x. If you were graphing this, well, all log graphs have which point? 1 comma 0, that's true for this one as well. What's this point going to be? E comma 1. All log graphs have an asymptote at x equals 0. And so this graph will be the graph of the natural log. And you'll be able to do transformations of the natural log graph as well. So if you want some practice graphing, you can do questions 10 and 11.